If p is a prime number and d divides p minus 1, then there are exactly 5d incongruent integers having order d modulo p. Now proof: let d divides p minus 1 and psi d denotes the number of integers k where 1 is less than equal to k is less than equal to p minus 1 that have order d modulo p. Since each integers between 1 and p minus 1 has order d, for the sum d divides p minus 1 is equal to sigma d divides p minus 1 psi d. Also, by the Gauss's theorem, we have p minus 1 is equal to sigma d divides p minus 1 is equal to phi d. Combining these are 1 and 2 equations. Combining 1 and 2, we get sigma d divides p minus 1 psi d is equal to sigma d divides p minus 1 phi d, equation 3. Now we are to show that phi d is less than equal to of psi d is less than equal to of phi d for each divisors of d of p minus 1. Given an arbitrary divisors of d of p minus 1, there are two possibilities: either psi d is 0 or psi d is greater than 0. If psi d is equal to 0, then clearly psi d is less than equal to of phi d. Let psi d is greater than 0, then there exists an integer a of order d. Then the d integers a square, so on, a raised to power d are incongruent modulo p, and each of them satisfies the polynomial's congruence. X raised to power d minus 1 is congruent to 0 modulo p, since a raised to power k into d is congruent to a raised to power d into k is congruent to 1 modulo p. By the corollary to the Lagrange's theorem, there can be no other solution of the equation 4. This is equation 4. So it follows that any integer having order d modulo p must be incongruent to 1 of a square, so on, a raised to power d. But only phi d of the just mentioned powers having order, namely those ak for which the exponent k has the property of greatest common divisor of k and d is equal to 1. Hence, in this case, we have psi d is equal to phi d, and the number of integers having order modulo p equal to phi d. Thus p is a prime number and d divides p minus 1, then there are exactly phi d incongruent integers having order of d modulo p.